In this video, we're going to look at the basics of writing your own .at2 assembly files for the AT-Robots program. Specifically, we're going to be looking at the types of statements that you'll find in an AT-Robot assembly program. We're going to look at assembler directives to tell the assembler how to do certain things with your programs or things that affect runtime. We're going to look at the structure of the source files themselves, how they're physically organized, so that we do things in a kind of standard way that people are used to seeing when it comes to assembly language programming. And we're going to look at the configuration point system of the AT-Robot, so you can see how to change the hardware of your robot to accentuate your strategy. And we'll look at the side effects of those configuration changes as well. So let's get to it. So the first type of statement everybody needs to learn when they look at a new language are comments. We use them in virtually all coding standards to put block comments at the top of the file to indicate who wrote the file, different times it was edited maybe, and what's the main purpose of the file. So in AT-Robots, comments all start with a semicolon. They can start on as the first character of the line, or they can happen later in a line to allow you to comment something that happened earlier in that line. AT-Robots has no form of block comments. You can just make several lines that start with semicolons. Now it's important to note excuse me, that if you are programming in a Linux or Unix type environment, that you need to make sure your text editor saves your .at2 files using Windows or DOS carriage return line feed line endings. Otherwise, whenever you hit a comment, the comment will appear to never end because the characters of the Linux or Unix system at the end of the line won't be recognized as new lines in AT-Robots because it's running in DOS. The second type of line that we have all over the place in assembly language programming is labels. And we have two types of labels in AT-Robots assembly. But what a label is basically a way, like a variable name, to allow us to avoid having to know the technical details of certain points of code, particularly where they exist in the memory of our robot program. So when we write variables or declare variables in our high-level languages, we do that so that we can say, I want to add 1 to I. I want to increment I in that for loop, rather than having to say, I want to take that thing that was at memory location, whatever, and increment that. Instead, we just use the variable name, and that's convenient. So in assembly language, we have no if statements. We don't have while loops. We don't have for loops. Instead, we just have to write instructions that tell the CPU inside the AT-Robot to relocate where it's going to run code next. So we have to tell it which part of the code, up here or down there, to jump to. And we identify those parts of the code not by which numbered line of code they are, because that'll change as soon as you add or delete code, potentially. Right? And we don't do it by address, because then we again have to know this specific location in the code, and that could change as we edit. So instead, like variables, we give code names by using labels to identify the code that immediately follows them. So in the example line on this slide, my label, which always starts with a bang, exclamation point, just looks like a traditional variable identifier. But if I were to put that on a line by itself in my code, it would identify whatever the next line of actual code to appear in that file, whatever address that line of code is at, will effectively become what that label is equivalent to. Right? And so that's very useful to us, because then we can refer to different lines of code. The second type of label is a numeric label, and I've noted here on the slide that these are special. And they are special because, excuse me, while you could jump to them by name, by identifying the number directly, they're much more useful in that if you make a label like this one, 295, if you have some fancy math somewhere that does some calculations and maybe sometimes comes up with a 295 and other times comes up with a 400, then if you have labels for 295 and labels for 400, you can make the mathematically calculated target of our jump to one of those two different locations without having to add any kind of logic that's similar to an if statement to say, oh, well, if we calculated this number, then go to this place. Otherwise, go to this separate place. Instead, we can just calculate the number and jump to any position in the code that has a label with that number. Now, of course, if we try to do that and there's no numeric label that exists for our calculation, then we'll get an error. But this is a very useful type of label, and it allows us to do things like the equivalent of a predictive time switch statement at the assembly level, right, or constant time, I should say. Excuse me. Another type of thing, of course, that you're going to see all through an assembly program are the regular instructions that tell the robot what to do. Most of these command instructions are formatted like the one listed here. There is a mnemonic that starts the instruction. It's a mnemonic in the sense that it's shorthand. In the ALU and control unit that we looked at in other lectures, we had instructions like INVA, which was just shorthand for invert the A register. In AT robots, we have the same kind of thing, and in most assemblies. So the MOV that leads this instruction, pronounced move, what that does, at least colloquially, is it moves the contents, or it moves the contents of some location or a number into some other location. In this case, what it does is it takes the number 64 and it puts it into the DX register. Now, virtually always in AT robots assembly, when we have these two arguments, and most instructions take two arguments, if there is storage involved, like do a calculation of some kind and store the result is typically going to be stored in the thing identified on the left, so the first parameter of the instruction. The thing on the right is typically just a source. There is one instruction, and we'll talk about it later, where this is reversed for whatever reason that Ed Toden had when he wrote this. Maybe it was just oversight. But there is one instruction where the order is swapped, but typically no one has a problem with that. Now, I did say this MOV instruction is short for move. Realistically, it's a copy. It doesn't take data away from one location and then put it somewhere else. It just copies the value in one location and puts it somewhere else. We can also define variables, and this is really our first assembler directive. The assembler directives all start with a pound or a hash, or SHA, I'm sorry. Here when we say pound def, we're effectively declaring that a variable of a particular name is going to be existing somewhere and used throughout the code. So in this case, we've declared a variable called my_variable. This informs the assembler only that such a variable needs to exist. It does not provide us the mechanism to put an initial value in that variable. It'll be initialized to the same value that all memory is initialized to in AT robots, which I believe is 0. But typically we like to write code that treats memory as if we don't know what's in it when we launch. But this just says that there is some memory location reserved for use by the variable name called myVariable. Then later in our code, we want to initialize it to 5. We could move into myVariable a 5, something like that. Now, before I move away from this slide, I do want to point out that in the command instructions, in between the two arguments, I've listed a comma here. I think the comma is good form, although the AT robots assembler does not actually require it to delimit between the first and the second argument. But it's typically used in a lot of other assemblers, so I like to keep it there, and it looks clean. So Now, excuse me, what I want to do is look at an example robot that has each of these things in it, and we're going to look at that same robot later in another video. And this is the Circles robot distributed with the AT Robots bundle I packaged up for the class. So you'll notice right away at the top of the file is a large, well, not block comment exactly, but a large series of line comments with information about the file, who wrote it, in this case me, and it's based on an original robot that was shipped with the official AT Robots package called Circles, written by Ed Toden. Excuse me. I just revised that particular robot to have a cleaner style for the purpose of these educational videos. We see the declaration of two variables, turn rate and chance, to be used for whatever their filthy purpose is later, but the code here defines those variables. We see a variety of instructions, and we see labels, and here's more comments. But what I want you to really notice is how this thing is structured vertically. There's kind of like pillars visually that happen in good formatted or well formatted assembly code. So on the far left, what we're going to have traditionally are the pound defs or other assembler directives. Pound defs for our variable declarations. We'll also have all of our labels all the way flush to the left. And in some cases, since there are a limit to the total number of labels that we can have in a program, 256 I believe, where we might otherwise have a label, we may also have left justified comments to indicate or at least suggest what a block of code that follows is actually going to do, as is the case with this line of code which says we're going to fire our weapon. Notice that all the instructions, which, here's a block of instructions here, they all sort of are formatted starting one tab's worth of spaces over from the left. Right? So all of them align to the same column, left justified. The same is actually true for all of my first arguments throughout the program. So the idea here is I'm just using my tab key, which my editor turns into spaces. It's really of no consequence in the context of the assembler here. But I'm ensuring that all of my instructions are the same distance from the left edge. And then each of my first arguments are just one tab after the mnemonic for the instruction. After I've done my first argument, I tab over as well. Now, as is the case in these three lines of code, you'll also notice that my second arguments are all aligned. That's true here, and it's true for these guys, but this set over here is in a little different place to the left from the other second parameters. I try to make sure that all my second arguments are aligned with one another within the same visual chunk of code. But since it's much harder to do this with the second parameter, I allow them to sort of fluctuate from left to right, but usually within the same block, like here. They are justified to the same column position. Assembly programmers love their code in columns, and that partly has to do with the earliest assemblers relying on the column to provide information, like something that was started in column 0 might be a variable or a register or something like that. There were rules based on these things, and it made the writing of an assembler simpler. That's where that comes from historically. Now also notice, much like the left edge of all my instructions, how they are justified to the same column, regardless of the length of all my instructions. I go through after my program is written, and I ensure that all the comments start at the same character column and at some multiple number of spaces based on me hitting the tab key. I want all my comments to line up as if it's a separate document that's been laid next to my code so that I can read it trivially from top to bottom, left to right, where scanning my eye back to the left side of the page, always goes to the same place, the beginning of those comments. Assembly code is not the easiest code to read. At least it's not nearly as easy to read as some higher level language code, right? So any kind of thing that we can do in terms of visual structuring that makes the code easier to follow, like making all of the comments showing up over here as if they're in one kind of document by themselves. All of that makes it easier to read the code that we've written, whether we're reading it because we wrote it or we're reading it because somebody else wrote it. So I highly recommend you follow that same pattern. All right, back to the slides. So here are some more assembler directives, and then I'll show code that uses these as well. So assembler directives are just statements that tell the assembler something to do at assemble time. They don't typically perform any action at runtime. So the two major ones we have are for messages and configuration options. For messages, if you do a pound MSG, and the case is not sensitive here with AT robots, when you do pound MSG and then follow that with some text string, the first 19 characters of that will show up in the status area of your robot at the time your robot is run. So an example of that is pea shooter. Let me open that up in my text editor. The pea shooter robot right here. Oops, I didn't mean to collapse that code. Right here on this line of code, it identifies a message, watch your 6, and then has a nice emoji or emoticon. So what happens here is at the time our simulation runs and the match begins, the little status area will say pshoot.at2, and then below it, it will identify this message, watch your 6. There's a robot called Mosquito that says, I'll suck you dry, and there's all kinds of other robots. There's a robot called Blockhead at one point that said something like, I am 2 + 2 = 4, whatever it is. So put any kind of shout out you want in these messages. If it's for the programming assignments that we have in my class, this is a place where I'll typically ask you to have your name printed out so that it's easy for me to tell what's going on as I'm assessing a grade. All right, let's go back to the slide. The second assembler directive we care about are the configuration options. So there are a number of different things that your robot has from a hardware perspective that affects its performance in any particular match. And we can change what those things are, or how strong or weak each of those different things are, by modifying how many points out of 12 total points are assigned to it. And for each of the different configuration options, we can assign a value between 0 and 5. But across all of them, they must add up to 12 or less. Less than 12 is fine, but no more than 12 is allowed, or your robot will be kicked out of the match, and the match won't run. So here are what the different options are. Remember this diagram from the previous video of our typical AT robot. Effectively, most of the elements that are there turn into some kind of thing that we can manage the performance of with a pound config. So one of them is the scanner, so we can increase or decrease the length of the scans that we emit when we're looking for other robots. We can affect the strength, speed, and heat generated by our weapon. We can affect our armor, how much damage it helps alleviate, as well as a sort of a negative side effect. As we increase the armor, our robot gets heavier, so it has a decreasing effect as we increase armor on speed. We can modify how strong our engine is, so we can go have a weaker engine and go slower at our top speed if we want, or we can have more points given to it and go faster. We can beef up or weaken our heat sinks. That affects the rate that we cool. We can increase the number of mines we have by default. We always start with 2 mines and no points associated with it, but we can beef that up to quite a large number of mines for whatever our purpose is. We can also increase the points contributed toward the shield And initially, no robot has a shield by default, but if you beef this up, then you can have a shield. Now, when we assign points to this, I'll go back to the previous slide. We write this out as pound config, then there's a space. We identify the configuration thing by name, then an equal sign, and then a number. There shouldn't be any white space around the equal sign. I think it shouldn't matter, but if I recall, there's still a lingering error that I haven't fixed in my version of AT Robots, where one of the configuration options doesn't work if there's white space on one particular side of the equal sign. So normally I just don't put any white space at all. But those are the configuration points that we deal with. Now, since they have to add up to 12 and there are default values associated with each of these, it's good to know what they are. And you can read about them in the AT Robots folder of the bundle I've given you in the atr2.doc file, the original AT Robots documentation. Now, I have not updated that file as I've made modifications to the AT Robots software, but most of the modifications I have done are just bug fixes to make it work the way it's supposed to, and not really functional changes. There is one case, but we'll talk about that in another video. Excuse me. So the default options are summarized here in this table. In this column we show how many points you could apply to a particular option between 0 and 5. And then in each other column we see what that particular configuration option is, and then what the different effects of the point distribution is. Where you see an asterisk in each of the columns, this identifies the default for each of the configuration options. So for scanner, it defaults to 5, weapon defaults to 2, armor defaults to 2, so does engine. Heat sinks default to 1, and mines and shield both default to 0. So when you write your code to change these values, you really have one of two options. I'll show it to you both ways. And I think one is clearly superior to the other. So the first option is what we see in the P-shoot robot. So here Ed Toten has manipulated the weapon, the scanner, the engine, and the heat sink configuration options from their default values. But that means he's had to track sort of mentally, and as you can see in the code, he's had to track how many points are associated or how many points he's giving up or getting back by making these configuration changes. So when he assigns a weapon value of 1, this is giving him a surplus of 1 point to put somewhere else. When he drops the scanner from 5 to 3, that gives him an additional 2 points. So he's got 3 extra points to work with. He gives 2 more of them to the engine, so he consumes 2 points, and he marks this in his comment. And then he gives 2 to the heat sinks, or 1 by assigning 2 to the heat sinks, he's increased that by 1 point. So he earns 3 here and uses those 3 back here. So this looks fine, and it works because he's keeping track of how he's changing the default distribution up and down. But really that means he has to know what those all are, and that information isn't in this source file, right? It's not there. It's in the documentation or the slide that I just showed you. And so it would be much nicer if the actual code identified all of the configuration options and how many points are associated with it. Then you could just add up the numbers in a column and say, well, does that add up to a number that's 12 or fewer? A great example of this is in Ed's wall bomb robot. So same author, just a slightly different technique. Here he lists each of the different configuration options in the code and assigns 0 to some and a number to the others. And then as we go down through all of them, we can just add them up. 5 and 3 is 8 plus 4 is 12. So we know, because all of them are there and they add up to 12, that this isn't going to result in the robot getting kicked out of a tournament or stopping a match from going forward. I think this is by far the better way to manipulate configuration points. So if you're not going to touch the configuration options and go with the default robot, don't add any pound configs to your code at all. If you're going to manipulate any configuration option, I highly recommend you take the example set by Wallbaum, list all configuration options, and assign all of them a literal value so that you know what's actually going on in that program, rather than constantly having to refer back to documentation or slides. All right, so what do these different effects do? So your scanner by default is 1,500 meters long, and since it's a 1,000 by 1,000 meter arena, if you are in one corner aiming at the opposite corner, a 1,000 meter long scanner won't see all the way clear into the other corner. So 1,500 one will. So by default, every robot has a scanner that's long enough to see anywhere else in the arena by length, no matter where it's located in the arena. So that's good. The weapon option is defaulted to 2, and the numbers that you see in this column are just scalar multipliers. So by default, if you don't mess with the weapon, you're going to get 1 times whatever the power, the heat, and the speed of that weapon is. But if you beef that up to 4 points rather than 2, then you're going to multiply whatever the base capability of that weapon is in terms of speed, heat, and damage by 1.35, so you're increasing its power. Conversely, drop it to 0 points and you'll get 50% speed, heat, and power. Damage, I should say, both that are inflicted. For armor, we have 2 columns. One of them is for protection, that's the left. So again, we start with a pair of scalars, both set to 1. If we were to bump our points from 2 to 3 for armor, then the left column, which represents the damage control, will increase our damage control by 20%. However, because we have better, thicker armor, it's also going to have an effect that's negative on our speed. So the right column is the scalar that's applied to our potential top speed. So we would multiply that potential top speed by 0.85, 85%. The engine column works very similarly. We've got a 1.0 scalar, and as we decrease points, we get engine performance that's less. Multiply this by the potential base speed of the engine of the robot. And conversely, if you give it more points, you can increase the speed. Now these are scalars applied to similar things, both from armor and engine. The right column of the armor is a scalar effect on your speed. So if you increase the armor, it slows you down. The engine column has a scalar effect on your speed. So the 2 multipliers are actually applied together. Excuse me. To make this crystal clear, let's say that you had, instead of 2 points assigned to both armor and engine, let's say you had 1 point assigned to armor, which means our engine speed will be multiplied by 1.2. It gets a little faster because we have lighter armor. And then because we want to use points for something else, say the weapon, we might also decrease our engine down to 0 points. So to figure out what a 1 point armor and 0 point engine top speed will be relative to the original top speed, we can just take and multiply 1.2 from the armor column by 0.5, and then we'll find out that the resulting top speed will be 60% of the default top speed. So we can apply that with any numbers. Let's say we want the fastest possible robot we can get. Well, we'd have to drop our armor as far down as we possibly can and boost up our engine speed. So if we dropped the armor all the way down, we'd have to have 0 points. That would give us a 1.33 scalar multiplied by say we increased our engine to 5 points, a 1.5 scalar, that's actually going to get us nearly double the top speed of the original robot, or the default robot. And you can make it go even faster than that. If you look further into the documentation for something called overburn mode, you can also increase the performance with another multiplier on your engine speed. And so you can get even more than twice as fast as the default robot. So that's pretty cool. So that's the basics for the types of lines that you're going to see in a file. We didn't really walk through the nature of all the instructions. We'll see that in another video. We did get to see all of the assembler directives as well as details of all the configuration options we can do to make a better robot. They can't change at runtime, so when you define these things, you're basically saying every match that this robot fights in is going to have these physical characteristics, and they're a lot of fun to manipulate.